almost to define this formula for me, Mr. Evan.
Velocity equals change in displacement over change in time.
Velocity equals a change in position over some time interval. I can also write this as the initial position minus the final position. We all know that, right?
Right. Yeah.
Excellent. So that means that I can also solve for any one of these variables. If I want to solve for its final position, I have everything I need. I know enough algebra to solve for it. Now, Mr. Evan, what about acceleration? Acceleration equals what?
Change in velocity.
A change in velocity over some time interval. Thank you very much. And so I can also write this as what, Mr. Evan?
What's that?
I can also write this as what?
Final velocity minus.
My final velocity minus my initial velocity, and solve for either one of these variables here. Excellent. Excuse me. Now, we have different kinds of motion that we've discussed this year. Name them all for me, Mr. Sean Thomas.
Come again.
Different kinds of motion.
Horizontal, vertical.
Horizontal, vertical. What kind of motion? 1D?
One-dimensional.
1D. 2D.
Projectile kind of motion.
2D with an angle. Projectile.
Projectile.
1D, 2D. And what else?
Projectile.
Projectiles.
Projectiles at an angle.
And projectiles at an angle. What are the different kinds of 1D motion? What's one kind that uses this dimension? The delta y dimension.
A rocket.
What's that called?
Projectile motion.
Freefall.
Freefall. Freefall is in the delta y direction. It's the kind of motions that we talked about this year, thus far. Excluding moving against some friction. This is what we've talked about thus far. Now, come now. I didn't want to do that. Free fall motion. In free fall motion, generally talking about an object dropped from some height to the ground. And anytime we're doing free fall motion, what is the acceleration of the object? Because it's free fall. If it was being thrown, it'd be different. If it had a rocket propeller attached to it, it'd be different. Free fall means that it's free from any other outside object, any other outside force. And its acceleration is what? 9.81 meters per second squared. I always know that. Now, in this case, depending on the convention, I can use negative, depending on what I'm looking for in the problem. It is negative. What does the negative mean? That it's going down. It's going in the negative y direction. Now, free fall motion is the same as any 1D motion. So any of the formulas that I used for 1D motion before, I can use for free fall. Can I not? Yes, just agree. So if I have a formula, for example, VF squared, we remember this one, equals VI squared plus 2A delta X. If I'm in the Y direction, what can I change? What must I change?
Change delta X.
Change delta X to delta Y. And there's another given that I use now. When I was moving horizontally, I had to find my acceleration. Here it's already given. And what is it?
9.81.
9.81 meters per second squared. Very good. Now,
Thank you.
the next kind of motion that we discussed after free fall, projectile motion, 2D motion. 2D motion assumes that we move in what two directions?
The Y and X.
The X and Y direction. 2D is X and Y. So one example of 2D motion is projectile motion. And we have two different kinds of projectile motion. We have projectiles launched horizontally and projectiles launched at an angle. Projectiles launched horizontally have some qualities. The reason why we did projectiles at an angle right after free fall is because it's very similar. Any object at any elevation, if it's launched horizontally, falls in the same amount of time as an object dropped from that height and dropped vertically. Follow? So if I drop a ball right here, they would both hit the ground at the same time. Because there is no change in their y direction. They both start at the same height and drop at the same rate, 9.81 meters per second squared. So if I want to know how long it takes for this ball to hit the ground, I can use any of my 1D formulas to find the time. One of them that I use is delta y equals BI plus 1/2 AT squared. And in the y direction, because you have to make sure when you look at these formulas, you look at what we're taking into account. I'm taking into account Miss Walker. What am I taking into account in this formula? What am I taking into account in this formula? What's this formula telling me? What are some variables that it's using?
Acceleration.
It's telling me that I need to take into account the acceleration. What else?
Velocity.
The initial velocity and what else?
Time.
It's time and what else?
The delta y.
Which is what? It's height. I'm taking height into account here. If this was delta x, I'd be taking my horizontal distance into account. All I've changed is the variable here. Now, what is the initial velocity in free fall? In free fall, zero. So that means that my initial velocity in horizontal projectile motion is 0, which cancels this out. So if I'm looking for time, this one, most of you remember. All this is solving for time in this formula. Because its initial velocity is 0. Solving for time, I get this. So I can find out how much time it takes to fall to the ground. The reason I can use this same formula again is because they fall at the same rate. The only difference in horizontal projectile motion and free fall is that horizontal projectile motion is free fall with an initial horizontal velocity. Now, does anybody remember when we drew this? Let me shorten this up just a little bit. Anybody remember that?
Yeah.
What is the initial velocity?
0.
But as it moves along, the velocity does what? It increases. What causes it to increase?
Gravity.
Gravity, until it gets to the ground down here somewhere. So there's a problem. Making sure there's a problem in the book, and there's various problems in your web assignment that you'll have more of. When it asks you what velocity did it have when it left the cliff, for example. This velocity is the same as this one, this one, this one, this one, and this one. The velocity is constant in the x direction because in a vacuum, there's nothing to oppose its velocity. It stays exactly the same. Follow?
Yeah.
So now the velocity stays the same all the way throughout. So to ask you for the velocity, you can find that using any one of those horizontal 1D motion formulas that you used before. But if it asks you what velocity does it hit the ground with, that's a different question. I know my x velocity. My y velocity, how can I find my y velocity? It's still, remember free fall. How can I find my y velocity? How can I find the velocity that it hits the ground with? I can change x to y, but I can use some formula.
VL squared.
I can use that one. VF squared equals VI squared.
Plus 2A delta x.
I can use that one. There's another one I can use. But I'll write this up here. So delta y. If I want to find the final velocity, in this case, my initial velocity would be what? 0. My initial velocity would be 0. You have to be able to visualize this and know what you're looking for. So I know my initial velocity in the x direction was 20 meters per second. And my final velocity, but I can use this because this is going to be my final velocity in the x direction too. All the way throughout. So it's always going to be my final velocity in the x direction. If I'm looking for my final velocity in the y direction, I'll solve for it using a formula like this. If I get the value 21 meters per second, what is my final velocity? What is the velocity with which this projectile hits the ground? 21 meters per second in the y direction, but there's still an x direction to this projectile. Who can beat me there? Beat me there. What do I need to do?
Say it again.
Anytime I have an x component to my velocity and a y component to my velocity. We've been doing x and y components for quite some time now. If I'm given an x component and a y component, what do you think it could possibly be asking for? What's up? The resultant velocity. This problem, and like problems you've done before, like the individual who kicks a rock off a seaside cliff at an initial velocity of 18 meters per second at a height of 52 meters, and it asks you what speed does it hit the ground, hit the water with. This is not the velocity that it hits the ground with, and this is not the velocity it hits the ground with. The velocity it hits the ground with is this one. And so how would I find this one? Say it to me again. Pythagorean Theorem. Yes. And we know, or if we didn't, we know now that when we're putting vectors together, even though this is giving my y direction, my x direction, when I'm adding vectors, we add tail to end. Because sometimes when y'all see it like this, you start making a triangle like this. which throws you completely off because that doesn't make any sense. Saying the projectile hits the ground, jumps back up, is asking for, doesn't make any sense. You have to be able to add the vectors correctly. Follow, Mr. Peterson? Very good. Now, the difference here with projectiles at an angle, because I got smart individuals in here, Mr. Thomas. Now let me ask Mr. Moulton, what is the difference between projectiles at an angle and projectiles launched horizontally?
Projectiles at an angle have a y.
Both of them have a y.
The y affects the.
Hurry, I'm running my recap time. What?
The projectiles at an angle have the x and y.
They both have x and y.
They have an angle.
They have an angle.
That's it.
So
That's
that means that this projectile has an initial angle now. So now it has a y displacement in the opposite direction. It always had a y displacement in the negative direction, but now it has a positive y direction, and it has a y velocity now. And so in the formulas, what do you expect to see in the formulas you use for projectiles at an angle?
X and Y.
Theta. Look at that. Mr. Smith is in the game. So that means that, for example, this formula that I had before now has an angle, VI sine theta, plus 1/2 AT squared. It includes an angle now. So now that it includes an angle, the same information exists. Where in here does it look like horizontal projectile motion?
Right.
When you like going across, that's the
Right here?
Right there. Yeah.
Right there.
And it is. So the only thing that I've really added into this problem is this portion. This initial portion, because from here on, my final velocity from this portion is my initial velocity here. And this is the same information that you would have had to know or to understand if you were trying to do the rocket problem. If you actually looked at the rocket problem, there was part of the problem where the rocket boosted the rocket booster boosted this rocket up to a point. Then it dropped off. And so whatever the velocity was when the rocket fell off is the velocity it started at here. That's why I said there are three portions to this. There's a portion that has a rocket boosted part when the rocket falls off, right here, and then when the rocket is gone. I'm sorry, not when the rocket is gone, but when it reaches the top of its height. From here, there's nothing boosting it, so it's nothing but horizontal projectile motion. And you'll see that problem again. Now, what I have for you is much fun today.
I don't like what we said.
Today, you have Uno quiz. This is your quiz. Please tear your half sheet of paper.
Is it 5 minutes?
You have 7 minutes this time because there's 2 of them.
How generous.
You have 7 minutes. You may use your notes and or your book. You may not use a phone calculator. You may not share calculators. Yeah.
Stop it.
Oh yeah, you can pause it.